Socratic math tutor here. We're going to find the cube roots of this complex number, and the task says that we should express our answers in polar form. So what that basically means is that our answer should be in the form r cis theta, where r is the distance to the origin, so it should be a positive number, positive real number, and theta is the angle from the x-axis going anti-clockwise. And so obviously theta has to be a real number. Angles are always real numbers. But more specifically, so if we look over here, we're told to use the principal values of the argument. And so what that basically means is that theta should be at most pi, and it should be at least negative pi. And so this condition suffices to ensure that there's a unique such theta for each non-zero complex number. So to get started, let's just give a name to the number that we're studying. So let z equal 1 over root 2 minus 1 over root 2i. As a general rule, if we need to find out some property or some attribute of an object, it's a really good idea to just give it a name. So that's what we've done here. Oh, that's a terrible arrow. That's what we've done here, just calling it z. There's the number. And it actually, the question says to express our answers in polar form. So technically we don't have to put this number z that we've just written down into polar form. However, in practice, it's a lot easier to find the nth roots of a complex number if it is in polar form. So that's what we'll do. And to do that, we're going to use the following theorem. So let's just talk through the notation for a moment. This C with an extra line through it, this is standard notation for the complex plane. So hopefully you know that. So this part is just saying, given that z is a complex number, and then we have our conditions. So here are our conditions on our theorem. So suppose that the complex number given is not 0. Then, according to this theorem, our number can be written as a product of its modulus times this extra bit. And what this extra bit does is it basically tells us the angle from the x-axis at which our complex number can be found, okay? And so specifically it's cis of this principal argument, this number that's, between negative pi and pi. So it's living in this, in that interval, okay? So to actually use this, we can just go ahead and start computing things. Let's find the modulus first. So the modulus of z by definition is the real part of z squared plus the imaginary part of z squared. And we have to take a square root of all of that. And so this is the square root of, so this is the real part, 1 over root 2. And obviously if we square that, we get half. So I'll put half here. And the imaginary part is negative 1 over root 2. So once again, squaring that, we get positive a half. And so this obviously equals 1. And that tells us that this modulus here, this is 1. So basically, because we're multiplying by 1 here, we can basically just ignore this part of the expression. We can ignore that. And so we conclude that z equals cis of argz. So all we need to do now is find the principal argument of z, and we'll have expressed z in polar form. Now to do that, there's a few ways of proceeding. I honestly feel like the least formal approach is the best approach. So just drawing a graph seems to be a really good way of just getting the job done at this point. So right, real of z here, im of z here. Technically, this is what's called an Argand diagram. Argand diagram. So that just means that we're plotting complex numbers on a Cartesian plane with the real parts depicted on the x-axis and the imaginary parts on the y-axis. All right, so let's have a look at the components. So the x value of z is 1 over root 2. So, well, we can go ahead and just, it's not a nice color, and just depict that right there, 1 over root 2. And the imaginary part is negative 1 over root 2. So somewhere there, negative 1 over root 2. And it should be fairly obvious that this theta here, this is pi on 4. So 45 degrees. That should be fairly clear just from the diagram. And so what that tells us is that the principal argument of z is negative pi on 4. So why is it negative here? Well, the principal argument is it's the angle anti-clockwise from the x-axis. And if you remember our diagram, we were actually going clockwise to get to our complex number. So therefore we pick up a negative here, and so the principal argument is negative pi on 4. So therefore, using this formula, we can finish off the problem, or we can finish off this part of the problem. We learn that z equals its modulus, which is 1, times cis of its principal argument, which is negative pi over 4. And therefore, the conclusion is that z equals cis of negative pi over 4. And this is kind of the halfway mark. We're halfway through the problem. Okay, so we've written z in polar form. However, before going on, I just want to give you guys something. But for those of you who do like a more formulaic approach and you're not into the diagrams, you maybe you don't feel they're rigorous enough, or you just don't find them that clear, there is actually a formula you can use. So I want to give you guys that formula. We'll just put it, actually, let's put it down here. And so the way this works is that basically what we need is we need a complex number with real part not equal to 0. So that means that, you know, we're kind of out here. We're not here on the imaginary axis. So we can be there, we can be out here, but we can't be on the y-axis in some sense. So given a complex number with real part not equal to 0, what we can do is we compute inverse tan of the imaginary component divided by the real part. And then we've got some correction things out there. So we might have to add pi. That's what all this is about. I'll explain that a bit more in a moment. And we also, this is not an equality, this is actually a congruence. It's a congruence modulo 2 pi. So let's spend some time just understanding what that all means, okay? We'll start off with this part. And specifically, I want to talk about this. So these brackets are called the Iverson bracket. Iverson bracket. And the definition is quite simple. The Iverson bracket applied to P. P is a Boolean, so it's either true or false. It's 1 if P is true, and it's 0 otherwise. Okay, so another way of saying that is the Iverson bracket applied to true is 1, and when applied to false, we get 0. Okay, so what's the point of that? So here's what's really cool about the Iverson bracket. Suppose I maybe want to add pi. If this condition is true, let's say I want to add pi, and if it's not, I don't want to add pi. Well, because multiplying by this is potentially going to be 0, and because it's going to be 0 if this is untrue, this whole plus pi times an Iverson bracket thing is kind of giving us a maybe plus pi. We're adding pi if this is true, because otherwise we just add 0, so it's like adding nothing. So that's what the Iverson bracket is used for. It just kind of cleans up our formulae a little bit. Now, the other thing that's worth talking about here is the meaning of this notation. Well, I'm really bad at actually pointing to things with arrows, of this notation. So hopefully you've seen this before, but if not, we'll just talk through it a little bit. So the question is, what does A congruent to B modulo C mean? All right, because that's what we've got here. We've got the congruent symbol here, and we've got the modulo out here. So what does that actually mean? So here's what it means. Well, let's go through some examples. So 1 is congruent to 6 modulo 5. And the reason is because by adding and subtracting 5, we can get from 1 to 6 and vice versa. So these are kind of accessible from each other by adding copies of 5, and therefore we say 1 is congruent to 6 modulo 5. In a similar way, so 1 would be congruent to 11 modulo 5. And the reason is because we can get from 1 to 11 and vice versa by adding and subtracting copies of 5. So another way of saying that is that A is congruent to B modulo C if and only if C is a factor of A minus B. So for example, over here, A minus B would be negative 10, And so because 5 is a factor of negative 10, therefore 1 is congruent to 11 modulo 5. There's another way of saying it as well that you might prefer. You might find it a little clearer. Another way of saying it is that a minus b is a multiple of c. It's a multiple of c. So once again here, looking here, a minus b would be negative 10. And so because this is a multiple of 5, therefore 1 is congruent to 11 modulo 5. Okay, so hopefully that clarifies what modulo means. Okay, so let's go ahead and use this formula. So we write arg of z is congruent to inverse tan of, now it's the imaginary part on top. Oh, that was weird. And it's the real part on the bottom. So obviously, if I have negative 1 over root 2 here, if I have 1 over root 2 here, okay, well, that really simplifies. It's really just negative 1 in here. So I just put that straight in. Negative 1 plus, now it's plus pi times this Iverson bracket. And the question is really whether real of z is less than 0. So just looking at the real component, it's clearly not. And so we can put false in here. False. And so what that tells us is that this is actually, it's 0. And so because pi times 0 is 0, therefore we're adding 0, therefore we actually don't need any of this, because this part is irrelevant, okay, because we're just adding 0. And then we just write modulo 2 pi to just remind ourselves that we might have to add or subtract 2 pi to get the principal argument. Now, hopefully you know that inverse tan is negative pi on 4. That's one of the values that you should essentially have memorized, more or less. Pretty helpful value. If you are a little bit confused about that, try to keep in mind that tan inverse of negative x equals negative tan inverse of x. So that lets you move things into the first quadrant, which is where you should have your key values memorized. And the reason for that is just because if we do plot inverse tan, we get a function like this that's kind of anti-symmetric across the y-axis. Okay, so I've given you two ways of working out the polar form of z, which is this. So let's go on and find the cube roots. Actually, it's helpful before we go on to get a little bit more notation going, because the nth roots notation is actually, it's a little bit ambiguous. So I'll make the following point. What is the fourth root? What is the fourth root of 81? Well, the standard answer is that it's 3, and that's a perfectly reasonable answer. But actually, if we want the fourth root of 81 viewed as a real number, we should keep in mind that there's really two fourth roots. So there's actually there's negative 3 and there's positive 3. Because if you take either of these numbers and raise them to the fourth power, you'll get 81. And these are the only real numbers that have that property. And it turns out that in the complex plane, there's even more of these things. So the fourth root of 81 viewed as a complex number is actually, so it's plus or minus 3. That's this set. Or so I'll put union for or because we're combining sets, or plus or minus 3i. Okay, so in other words, our solutions are negative 3, positive 3i, and negative 3i. So there's actually 4 fourth roots of 81 in the complex plane. And so therefore to know what our answer is, which of these is applicable, we kind of need to know where we're working. We need to know the context. And so this notation I use here with the two dots just kind of indicates that context. It tells us where we're taking our nth roots, okay? Okay, so remember, the task was to find the cube roots of z viewed as a complex number. And therefore using, actually want this to be green. So using this knowledge we've got here of the polar form, we can say that we're trying to find the cube roots of cis of negative pi on 4, viewed as a complex number. And to do this, there's a theorem we can use. So it looks a little bit complicated, but it's much simpler than it looks. So let's just go through it one bit at a time. So here's what we're trying to find. It's the nth roots of cis theta viewed as a complex number. That obviously is the form of the thing that we're trying to find. And we're told by this theorem that the answer will be, it's going to be a sequence of numbers, w0 up to wn minus 1. N is the degree of the root we're taking. So in this context, n is 3. So our solutions will be of the form w0, w1, w2. And the formula for these w's is given on this line. Okay, so let's just talk about some of the symbols here because they might not be familiar. So this upside down A, this is the for all symbol, for all. And so therefore what this line is saying, oh, and by the way, this symbol here, this Z with an extra line here, this is the set of integers, right? So these numbers, -2, -1, 0, 1, 2, etc., right? So basically whole numbers, but we include the negatives. So -5 is an integer, for example. So therefore we can read this line as follows. For all j in the set of integers, w subscript j is defined to equal cis of this expression. Okay, so for all integers j, w subscript j equals this expression. Now, where is this coming from? So we're trying to find the nth root of cis of theta. So we start off with cis of theta. We're trying to find the nth roots. So we do cis of theta over n. And this gets us one of the roots. But to get the others, we have to add copies of 2 pi into the numerator. And that's what this 2 pi j is doing for us. So it's getting us all the other solutions. Okay, so let's just move this out of the way. We'll put it up here. And according to this theorem, this thing we're trying to find, this equals w0, w1, w2, where wj equals, and we use this formula, right? So this n is going to become a 3 because we're taking a cube root. Nothing else really changes, so we can basically just copy it. Wj equals cis of theta plus 2 pi j over 3. And we actually know what theta is, right? Because this is our theta. And so we can, if we want to, we can actually just put it straight in. It's probably, I think it's a bit clearer actually to put it straight in. So put negative pi on 4 there. And these are our wj's. And so we actually wanted to find this for all j in the integers. Or if we wanted, we could just define it for j in 0, 1, 2. That would also be okay. But it's a little bit less notation to just put this z in. Okay, so let's go ahead and simplify these wj's now. Let's change color. So w0 is cis negative pi on 4 plus 2 pi j. The j is 0, so we don't need it. So it's this divided by 3. And so this just simplifies to cis of negative pi over 12. By the way, the number one way of making mistakes here is to actually try and jump to something like this. So you put 12 in the denominator, and then you just end up really confused about what needs to go into the numerator. So don't go straight to that simplification. Actually, use this theorem. It's a really good theorem. And that way you won't make silly mistakes, okay? Okay, let's go ahead and find W1. So this will be cis of pretty much the same thing. Pretty much the same thing as above, but we have to add 2 pi here because j equals 1 over 3. And let's just clean it up. So negative pi on 4 plus 2 pi. That's going to become negative pi on 4 plus 8 pi over 4 plus 8 pi over 4 all over 3. This will be cis of, So negative pi plus 8 pi is 7 pi. Over 4 over 3 is over 12. And so there's our W1. That's our second solution. Finally, we'll go ahead and compute W2. I don't know if we've got enough space, but we'll do our best. I'll tell you what. So we're going to just emulate the previous line. Negative pi on 4 on top. Now we add 4 pi here. Still over 3. Just to save a bit of space, I'm gonna jump a step. So we're gonna end up with 15 pi over 12. It's probably 2 steps in there. I've missed a cis. Over 12, this simplifies to 5 pi over 4. And because this is because it's too large to be the principal argument, we can just subtract 2 pi from inside the cis brackets, inside these brackets here. And when we do that, we get, well, if we subtract pi, we get pi over 4. Subtract pi again, we get negative 3 pi over 4. So these are our 3 solutions. And so we conclude that the cube roots are in polar form cis of negative pi over 12, comma, cis of 7 pi over 12, comma, cis of negative 3 pi over 4.